Graphing exponential functions. I encourage you to go use Desmos and do a little bit of exploration. You'll get to Desmos by typing in www.desmos.com/calculator. All right. When you're in Desmos, you want to type in exponential functions starting with y equals 1 to the x power. Just see what you end up with. Then change that to y equals 2 to the x power and see the difference. Well, then you can change that to y equals 3 to the x power and see the difference. Well, then you can change that to y equals 5 to the x power and see the difference. Well, then you can change that to y equals 1/2 to the x power and see the difference. Y equals 1/10 to the x power and see the difference. Y equals -2 to the x power and see the difference. Y equals -2 to the negative x power and see the difference. Now, as you see, you can obviously keep going and going and going and continue to type different numbers in just to see how the graph is going to start to change. We'll talk about transformations a little bit more next week. So we're going to add to these particular equations, but all of these are basically using a base raised to a particular power. And so that's what we're going to graph now. So I have talked to you about graphing in the past, and we've determined that we can graph anything using a t-chart. And so a t-chart is basically an XY input-output table that gives us our ordered pairs that we can graph on a graph. Now, I recommend that you use your -2, -1, 0, 1, and 2 as your inputs. And with exponential equations, I like to start at 0, work my way down, and then go back and work my way up on the negatives. So the reason why I start with 0 is because when we plug in 0, 3 to the 0th power, it equals 1. Anything to the 0th power equals 1. So that becomes an easy ordered pair to identify. So 0, 1. All right, let's plug in the next ordered pair. 3 to the first power is 3. So we have an ordered pair, 1 up 3. All right, our next ordered pair, 3 to the second power is the same thing as saying 3 times 3. Well, that's 9. So we come over 2 up 3, 6, 9. Now we can see from the graph that starting at our first ordered pair 0, 1, it's moving up and then moving up much faster, and then obviously going to move up really fast from there. Well, so far that's just what happens when we go into the positive x values. What about when we go into the negative x values? 3 to the negative first power. Well, 3 to the negative first power has a negative power, and we can't have negative powers with exponents. So in order to make the power positive, we bring it across the fraction bar, 3 to the first power, which is just 1 over 3. So we end up with -1 up 1/3. Yes, you're going to be approximating where 1/3 is on the graph. It's not going to be an exact science, but you're going to get a good feeling for what the graph will look like. All right, -2. 3 to the negative second power. Again, you can't have a negative power, so that ends up with 1 over 3 to the second power, which is 1 over 9. And 1/9 should be much closer to 0. Now, if I continue to plug in negative values, say -3, 3 to the negative third power is equal to 1 over 3 cubed, which is equal to 1 over 27. Notice I'm getting smaller, and I would continue to get smaller and I would continue to get smaller, and I would continue to get smaller, but at no point would I end up with a number less than 0, because every negative power that I plug in is going to end up with a 1 in the numerator divided by an ever-increasing value. So as the denominator continues to ever increase, it gets smaller and smaller and smaller and approaches 0, but never touches the x-axis. That's our first exponential function. Next, f of x is equal to 1/2 x. Well, we're going to do the same thing. We're going to have our xy input-output table, -2, -1, 0, 1, 2. And so I'm going to start with 0. 1/2 to the 0th power is 1. All right. 1. So 1/2 to the first power is simply 1/2. So we come over 1, up 1/2. Already we can see going from left to right, we are declining. Well, that's because this value of our base is less than 1 but greater than 0. When you have a base that's less than 1 but greater than 0, we're going to identify that as decay. And it's going to cause our graph to be decreasing. So let's keep going. We'll plug in a 1 for x. 1/2. Oh, sorry, we already did that. Let's plug in a 2 for x. 1/2 to the second power. Well, that's the same thing as saying 1 to the second power over 2 to the second power, where 1 to the second power is 1, and 2 to the second power is 4. So we can go over 2, up 1/4. And we're starting to see, hey, I've got a pattern where these values are getting smaller and 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 smaller, but never crossing the x-axis, always staying just barely above it. All right, let's plug in negative values for our exponent. 1/2 to the negative first power. Now, practically speaking, what's happening is we have 1 to the negative first power over 2 to the negative first power, where in order to make the powers happy, we have to bring them across the fraction bar. So we end up with 2 to the first power over 1 to the first power, which is simply 2 over 1, or 2. So we come back 1, up 2. Now, once we get used to this, we can shortcut it a bit. Notice my fraction 1/2, when raised to a negative power, becomes its reciprocal, 2 over 1. So we can do the same thing with our 2. 1/2 raised to the negative second power is going to be equal to the reciprocal 2 over 1 raised to the second power, which is equal to 4. So we come back 2, up 4. Now this graph's a little bit low because we don't have very steady decay or very quick decay, so it might be advantageous to give us a third negative power so we can see what's happening as the graph comes further to the left. So that would be 1/2 to the negative third, which is the same as 2 to the third power, which is 8. So if we come back 3, we come up 4, 5, 6, 7, 8. That puts us a little bit closer to the top of the graph. Gives us a good indication of what's happening to this graph as it goes up. This is what we consider, again, exponential decay. Reading from left to right, the graph is decaying or getting less and less and less as it approaches 0. F of x is equal to 2 times 1/4 to the x power. Well, notice this is no longer just a base raised to a power. We're now multiplying that base by a value. Well, same process. We plug everything into an xy t-chart. -2, -1, 0, 1, and 2. So we have 2 times 1/4 raised to the 0th power. Well, 1/4 to the 0th power is 1, so we're down with 2 times 1, which is, 2. Notice this is the first graph that we did not end up with an ordered pair at 0, 1. Rather, we ended up with an ordered pair at 0, 2. Now, why did we end up with an ordered pair at 0, 2? The reason why we ended up with an ordered pair at 0, 2 is because this value here doubled our 1/4 to the 0th power. Well, we felt like we saw that in some of our previous units. Yeah, in quadratics, we had values that doubled it. In linear equations, we have values that double it. So essentially what's happening is that value right there is stretching vertically our graph. We've talked about that concept before, and we'll talk about it a little bit more when we talk about characteristics and transformations of graphs. All right, let's plug in a 1. So 2 times 1/4 raised to the first power. Well, 1/4 to the first power is 1/4 times 2 is equal to 2/4, which is equal to 1/2. Okay, we go over 1, we come up 1/2. Now, we could have already predicted that this graph was going to decrease simply because the base value for the exponent was less than 1 but greater than or equal to 0, which results in a decay. Let's keep going. Let's plug in a 2. 2 times 1/4 raised to the second power. Well, 1/4 raised to the second power is the same as 1/4 1 to the power of 2, 4 to the power of 2, which is equal to 1/16. Well, we haven't multiplied by 2 yet, so let's bring that down. 2 times 1/16 gives us 2/16, which equals 1/8. So we can come over 2 up 1/8. And we can see this graph is very quickly going down, but again, it will never pass 0, 0. Now, you're probably thinking, Mr. Gable, it looks like your graph comes up a little bit. I am not going to nitpick at you guys having your graph come up just a little bit, because it's really hard sometimes to draw a straight line and keep it straight trying to come across the screen. It's not always any easier when you're doing it on a piece of paper. So I will give you a little bit of latitude if you can give me a little bit of latitude. All right, let's plug in a -1. So we have 2 times 1/4 raised to the negative first power. And what we learned from our previous problem was that the negative power is going to invert or flip our fraction. So we can bring down the 2. We end up with 2 times 4 to the first power, which is equal to 8. All right, let's do it again. We have 2 times 1/4 raised to the negative second power. So again, we're going to flip the fraction. So we'll end up with 4 squared times 2. 4 squared is 16 times 2 is equal to 32. Now, you should be thinking, Mr. Gable, there is no way -232 is going to show up on this graph. What do I do? Well, -232 doesn't show up on the graph. Don't do anything. Graph the ones that will fit. So we come back 1, up 2, 3, 4, 5, 6, 7, 8. That's the last one that's going to fit because this graph is growing really fast, or sorry, decaying very fast. All right, I want to get to one that has a negative. So now we have a -2 in front of it. Well, we're still going to solve the same way. We're going to use a t-chart, x, y, where we plug in -2, -1, 0, 1, and 2. So let's start with plugging in 0. 2 to the 0th power times negative 2, where 2 to the 0th power is 1 times negative 2 is equal to negative 2. So we go to negative 2. Well, that's a little bit different. We've not really ended up with a y value that was below the x-axis. Let's keep going and see what happens next. All right, so now we want to plug in a 1. Negative 2 times 2 to the first power. Well, 2 to the first power is 2 times negative 2, which is equal to negative 4. So we go forward 1, we go down to 4. That looks a little different too. All right, let's see what's next. Negative 2 times 2 squared. Well, 2 squared is 4 times negative 2, which is negative 8. So we go forward 2, we go down 4, 8. All right, let's see what happens when we put a negative 1 in. Negative 2 times 2 to the negative first power. Well, 2 to the negative first power is 1/2 to the first power, so times negative 2 equals negative 2 over 2, which is equal to negative 1. So we come back 1, down 1. Let's put our last ordered pair in. Oh, let me finish filling my table in. Apparently I've been skimping. All right. Negative 2 times 2 to the negative second power, which is 1 over 2 to the second power times negative 2. Well, 1 over 2 to the second power is 1/4 times negative 2, which is going to be negative 2 over 4, which is going to be negative 1 over 2. So we come back 1/2, and we can now very clearly see a direction or a pattern for these ordered pairs. Well, that's a little bit different, isn't it? It appears to have, it's not up here anymore, and it's not decreasing up here. Rather, it has reflected over the x-axis. Well, what caused it to reflect over the x-axis? That negative value right there caused it to reflect over the x-axis. And that will make a lot more sense when we talk about characteristics of functions. But for right now, I just want you to be able to put into a t-chart your x values, get out your y values. Again, show me your work, please, so I can see what you're doing, just in case you make a mistake. I really want to see steps that go along with your t-chart. Hopefully that helps you to do some graphing. I'll have an answer key posted to Weebly for you to check your answers.